Hello, everybody. It is Sam, the Reclaimer developer, and it has been a while since I've made updates of any kind, and I'll just tell you, it's been quite a whirlwind. My family has just been like non-stop sick since October, and like our entire holiday season was just absolutely obliterated by sickness. I decided not to make this a live stream just because, just with everything going on, I did want to have a chance to, think about what I wanted to do, without potentially having an audience, like, as I've had in the past, like, one or two people showing up, but even still. I have mentioned that I've been working on a game called It Flies By. Now, the Reclaimer is not going anywhere, but It Flies By is sort of taking precedence because it's a game that I'm making for my daughter. And it's very much inspired by the fact that, things have happened since I've started the Reclaimer. I'm a dad now. And the point of It Flies By is to, basically live life while you have it. And to not let, just don't let opportunities and chances pass you by. Don't live life saying, man, I wish I did that thing, And let me go ahead and be respectful of my audience and put myself on Do Not Disturb. My daughter's been very sick, and my wife's taking care of her right now, so you may hear her just kind of fussing in the background. She's doing okay, she's doing much better, but I'm not going to get into the details, but just, oh my, oh my damn, like, things have just been going on, and, the poor kid's been through a lot. So, all of you are actually going to get to see the It Flies By codebase today. And I wanted to talk about memory management. I've done this in the Reclaimer a little bit, like talking about how I've wanted to manage memory. But this time I'm actually doing things a little bit formal. And I have thought long and hard about how I wanted this engine to be designed. But I keep flip-flopping on what I want that to look like. I've thought about having a structure of, like, do we have, like, one executable and that's it? Or do we have just the executable plus, like, the engine library and the game library, which is the architecture I've settled on, but as far as, like, the APIs and libraries and stuff, originally everything was just sort of put into the engine, and I've also got my dog in here. Guy, come here, girl. Come here. And she's just fussing. And you can also see I'm kind of working with this sort of like backdrop setup. We'll just see how it works. But so how I've wanted to do things. How I'm doing things now is just basically, there's going to be a bunch of different libraries. And, the memory library is going to be one. So it's just going to be, memory library. And so I do want to be specific when I say, like, what does it mean to have a library? It just means that it's data in, data out, design. So there's going to be things that the library does control, but by and large, it's going to be up to the user, or the programmer rather, to say, here's a chunk of memory, and here's how I want you to basically use it and divide it up. And so it will just manage that chunk of memory however you tell it to, right? And so there's also like like it will use something that's called the platform API. And what the platform API is just a way to, anytime we have to send requests to the OS. That's it. It's very simple. And it's mostly around resource management. And memory is a resource, right? And so are files. So are, well, I wouldn't call user input a resource, but no, I wouldn't say that's handled by the platform. But we're also threads. Those are another resource. And, there may be a few others. So it's basically anything that the operating system would have to divvy out. And we want to basically make requests in such a way that we don't have to worry about platform-specific implementation inside the engine or the game. We basically just say, hey, I want to use this platform API, give me a chunk of memory. And so depending on the platform that it's working on, like Windows or Linux, or let's say if it was on the Xbox, it may do something different, or if it was on the PlayStation or the Wii, whatever API that is handling memory management, it will do that. So that way we don't have to worry too much about the platform-specific implementation. But right now, it's just Win32. Which is just Windows, right? We're using the Windows API to do all of these. And so there's a semantic that what we're doing here is there's two keywords here, right? Two keywords. There is a reserve and commit, right? So there is a, what's the difference, right? So a reservation is, it can be released, you acquire, that looks more like a Q. I think there's a C in there, I don't know. Acquire for time, and then release when done, right? And a commit is basically, I have this resource that I've reserved, right? And so somewhere in there, I want to subdivide that resource into two things that I need. And a commit is basically, I want the pin, like subregion, and it's immutable, right? And so that basically means for duration of resource. Like the semantic that we as programmers, at least low-level programmers that are used to the concept of managing memory manually, is, I'll just say like old semantics. Old, or we could just say old. For every new, there's a delete, right? And that is sort of like the normal way of doing things. And what I'm calling here is, in this context, is reserve and release, right? And so this could also be like with files or threads or, basically any operating system resource. I want to acquire it for some time. I want to reserve it and say, hey, this is a resource that I'm using, but I will release it when I'm done, right? But a commit says, I'm committing this, and it is constant. And the only way this goes away is when the entire resource is released, right? So you can reserve something and then release it, but when you commit something from that resource, you basically make it constant, right? So I'm introducing a new semantic here, and I will proceed to like show more of what I mean. So in the context of memory, so memory life cycle, right? So I want to call it a life cycle, or let's just say lifetime. There we go. Lifetime. Okay? So, memory lifetime is, so basically, game start, or rather, I would say engine start, right? Because the engine is going to be the thing that's controlling, memory requests from the game. It'll be basically, the engine reserves a chunk of memory, it passes it to the game, and there may be a few options like, hey, here's a stack of memory that is available this frame, here's a stack of memory that's available for the next frame, here's like a stack of memory that's available for this scene that's being executed, so on and so forth. And if it's not enough, the game can say, hey, I'm gonna need a little bit more, give me a little bit more to work with, right? So, but anyway, we're just gonna say engine startup, and we request all, I want that to be like an all caps, all memory we need, right? And so this is also a reservation, right? We basically reserve memory, right? So, and at the time, as of making this video, the memory footprint will go down, but there's going to be a lot of extra debug contexts. Like, I may have tools that allow me to like introspect into how things are being done. But right now, that reservation size is 4 gigabytes, right? So, and this also goes in, like the reserve, release, commit syntax also works with the Win32 API, because when you virtual allocate resources, specifically memory, what that does is I basically have this contiguous space in memory. I would also say virtual. Right? So, what does this look like? So, I'm just gonna say, we have our, that's a horrible, let's see if I can do better than that. Oops. Hang on. I am just all over the place tonight. I cannot, there we go. I cannot even, how does one, I did it again. I did it again. All right. So, I'm trying to find the doggone, tool that will let me, draw shapes, right? Okay, here we go. So, I just want to draw a rectangle. There we go. Right? That's the prettiest rectangle I've ever seen. So, basically, we have our reservation, right? And so, this says reservation start. And so this would be basically a pointer, right? And you could also just say, 0. And so this is reservation end. Right? And it's at, 4 gigabytes. Basically, 10 to the 24, 4 times 10 to the 24 times 10 to the 20... 4 times 1024 times 1024 times 1024. That's basically what the address space is that we're working with. And so this is managed by the OS, right? OS virtual memory. So what's neat about this is, I've done this before, so I'm not going to do it again, but if you go into, basically if you have, I think it's Process Explorer, and you look at the pages of memory that are reserved, if I say, hey, I want to virtually reserve this much memory, it'll be there for you. And here's the neat thing. I've only got 32 gigs of memory on this system, but if I say, hey, I want to reserve 128 gigabytes, it will do that, and it will not fail. It will just say, hey, this is the range of addresses you can commit to. Like, it doesn't show up as actual, like, used memory. But, and I'm just going to clarify reservation. This is a reservation, right? Now, but what I can do is I can do offsets from that and make commits, right? And so I can say this right here is commit 1. Or for programmers, we're going to say commit 0, commit 1, commit 3, and so on, right? And so I'm going to say commit in right here, commit in. However many commits, right? And so these are distinct regions of memory, right? And so right here is my committed memory. I hope I'm spelling that right. I'm engineer, I know can't English. Right? And we'll say, I don't know, let's say for the time being, this is 128 megabytes. It's divided up amongst the different systems that's used in the game, right? You've got a rendering system, you've got an asset system, you've got audio, all that kind of stuff. So this is the resources that are being committed. This right here is what's going to be showing up as used memory. So if you were to open Task Manager and look at the executable for It Flies By, and this was the memory that I had committed, that's what you would see showing up as, here's my actual committed memory. But I still have all of this available to me that I can just continue to commit from. So now it comes to, like, I think it's like a system like this is pretty flexible because I just say, here is all I would ever need, right? This is like the upper range, the upper bounds for, like, I'm calculating there will never be any way that that It Flies By will need more than 4 gigabytes in a debug context. I'm gonna try to shrink it and compress it for when it's ready for release, and hopefully try to get it under 2 gigabytes. But we'll see. But for now, I'm gonna have other stuff going on, things to monitor performance and other debug tools, so we're just gonna say we're gonna reserve a wumbo amount of memory, right? 4 gigs. So what are these? What are we calling these units right here, right? And so what I'm calling these right here is an arena, right? And so let's go ahead and talk about the memory arena. And I did not come up with this concept. There's plenty of talks by Casey Muratori of Handmade Hero Land. There's Ryan Fleury of Epic Games via the team that manages Unreal. He works for the Rad Game Tools team over there, and he did an excellent talk on memory arenas. And the easiest way that I can summarize quickly what an arena is basically a sandbox. Or sandboxed region of memory, right? So if you think about what a sandbox is, right? It's just a area where there's stuff and there's kids, or they're playing around, and they've got poorly made okay, we'll call that a shovel, and we'll call this a bucket, right? A little bucket. And the kids are playing, and the toys are in the sandbox, and basically stuff that's happening out here is not really a concern, right? But the sandbox has very fixed regions, right? It has a fixed set of dimensions, and the sand stays in the sandbox, and everything that happens there happens. And recess is over, and so what happens is all the toys are put away, and the sandbox is just totally clean. Well, an arena works exactly the same way. So it has fixed size, which is another way of saying arenas are committed, right? And which also means they're immutable. We can just say constant, right? They cannot be resized. Okay, so this is where this requires a little bit of intuition and context, right? So you would basically want to say, okay, I want the audio system to have 128 megabytes of memory to play with, and so on and so forth. Like the rendering system may have a gigabyte, or the entity in the physics system may have another 64 megs, whatever. We're just going to say context, right? And we can also say has a lifetime. What does that mean? Well, how can something that's constant have a lifetime? Well, it can work like this. So I basically have, it works exactly like this up here, like the sandbox, right? So you have kids coming over to play. And so one of them builds a sandcastle, and another one, wants to dig a hole, and another one wants to use like a toy tractor and stuff like that. And then it's like, okay, the bell rings, recess is over, and then basically everything gets wiped clean. The toys are put away, and you basically have just a clean, crisp sandbox. I mean, sandboxes are never clean, but I'm just saying within the context of this illustration. But the sandbox is still a sandbox. It still has the same dimensions. It still has the same things that you can do in it. And the next time the kids come out to play, they're going to do something entirely different. It's still the same resources that they can deal with, but it has a contextual lifetime, right? So a context and a lifetime are sort of linked together. And we can just say contextual. I was hoping to use that little scratch there. Contextual lifetime. And just basically what this means is that we don't have to worry about, like for every new, there must be a delete. None of that, right? So you basically say, I want to put this onto the arena, I want to put this in the arena, and then maybe there's some context where thing changes, right? Like you load a different level, or you load a different soundtrack, and you just say, wipe everything clean that I just put in there, and just start over, right? This way, you don't have to keep track of every new there must be a delete. You can just say, I do push, I want to push this, or, we'll just say push X, push Y, push another Y, push Z. And then, we load a new level. Just reset, right? Then I may push an A, push B, push C. Then we load another level. Load level, and you guessed it, reset. And here's what's really cool about this. All of this memory has been committed, we're not changing the context of the program from user mode into kernel mode. And what I mean by that is we're not asking the operating system to request resources from the computer. They've already been committed. So we basically just say, reset the, whatever the stack pointer is in that arena, reset it back to 0, like that. Everything's clear, and we don't have to worry about it. So how do we do this? Basically, we have an A, we have a B, we have a C. We can just say custom allocators. Right? And so the allocators represent the kids who want to come and play in the sandbox, right? So one wants to play with a tractor, one wants to build sandcastles, the other one just wants to dig, right? With bucket and shovel and all that. And so they just do whatever they want, and they just divvy up parts of the sandbox however they want to. And, the size of the sandbox determines how much they can do, but we just say, an allocator could be like... there's two that I really see beneficial within the context of It Flies By. There's block allocators and stack allocators. Okay, so let's go ahead and say we're just going to say block allocator. I'm trying to keep an eye on the time because I know I've been doing this for a minute. And this is just an overview anyway. We may look into this a little bit fuller later. Right? So, a block allocator is just basically say, both of these are fixed size, right? We say, here is how much I can allocate. We say, block of X size, and then we say Y blocks, right? And so what that means is I say, we say memory size is literally just X times Y, right? And so now what that does is that creates, basically we have these regions of just say we have X sub 0, X sub 1, X sub 2, and then X sub Y. And where this would be useful is let's say the asset system. Let's say an asset can be a maximum of 64K, and it would be 64K, 64K, and I can have, let's say there is Y in this case would be 1024. 1024 times 64K would be 64 megabytes, right? So at max, I can have, that many assets loaded at one time. That may be absurdly huge, but, we're just making an example here, and the power 2 math is easy. So, and what we say is, okay, I need to load an asset. So this one becomes reserved. Oh, I need to load another asset. So the next one is free. This one becomes reserved. And let's say I don't need this asset anymore. We just say, okay, now we don't need, we don't need this anymore, and we don't need this anymore. And as things are freed, they just become available, and we just grab the first one that's available, right? And we just put our stuff in there. And it can also have basic controls like reset, where it's okay, I don't need any more of these blocks, just reset all of them, right? And that just basically means they're free. We don't have to clear whatever's in there. We just say, hey, the memory, this block is free for you to put stuff in. Simple enough. And a stack allocator is first in, or no, let's do it this way. it's it was a little counterintuitive to say it like that. It is last in, first out, right? And what we say is, you basically just push, pull, and reset. This is the simpler of the two. I probably should have started with this. It's very simple. Very simple and flexible, right? This could just be a general area of memory that we have in our arena. And here's how it works, right? Here's our stack. And you can just say, okay, I need to push an X onto the stack. Now I need to push a Y onto the stack. Now I need to push a Z onto the stack. And then when this is all done, just reset it. And that context could be like, I'm starting a new frame of execution in the game. And so there may be a calculation that AI needs to do. The user moves really fast, and so Jig, the little companion character, is moving about, and he's moving fast, and, maybe that, for whatever reason, the calculation to do that requires more memory. It shouldn't, but, sake of argument, maybe the sound changes, and it's a bigger sound, so it's loading, more stuff, and then it's over, and we just reset it, right? And so there's a common thing that all of these have, right? No fragmentation. And this is another selling point of this type of memory management, in that doing things this way, it's like over in the block allocator land, we have all of these blocks of exactly the same size. So when we're done, we just put something back and we say, hey, this block is free or this block is used. And when it comes to the stack, we can push things of different size onto it, and then when it becomes full, we just either request another stack, or we just reset it and start over. There's other different types of allocators and data structures that we can use, but because It Flies By should be a very simple game, I see this as being like the only two allocators we really need. We push stuff on, we remove stuff, or we say something's available and something's not. And these are also static, right? We basically say they're also, and they're constant, right? Maybe that changes within like the context of how things work, but for now we're just going to say that these allocators are constant, right? And by fragmentation, it's like we're never going to have space that's like in between things. I may as well just illustrate it. So if I have this block, I allocate this, and then I allocate one of these, and then I allocate one of those. And so later on, and so I free things, I free this, and then, I have something here, but then this is gone, and I have this. It's like there eventually can be stuff in here that nothing can fit in, right? And so you have this unusable space. Everything is uniform, everything is constant, everything's pre-allocated. It is very fast and very efficient. We make sure that all of our data is packed together. There's no voids where something can't fit, and that's just how it be. Now, what I'm gonna do now is say, Alright, so the thing about where I'm at right now, and yes, we are finally getting to some code, right? That's what we want to see. We want to see the code. Well, this is kind of a mess because I've been just waffling back and forth on like, what the hell do I want to do with this, right? So, and that's where I'm still, kind of going back and forth on. And what I'm going to do is say get fetch all, right? Yes, I did mean that. So I'm gonna git check out it's the memory lib, right? I already have a memory library in here, but what I want to do is sort of like separate the major libraries into their own little units and have the engine sort of like utilize them however it wants. So let's go ahead and launch our handy dandy code editor that I'm using against my will, or rather, I would rather use something else, but I do not have the time to learn something else. Like, even my wife, she hates VS Code. She does DevOps stuff. I can't really say what she does for, security reasons, but she tried using VS Code and she hates it. And I'm like, love, I don't blame you. So, this doesn't really work, right? And I just want to, I hate saying it that way, but, here's, like, what I've got so far, and, I've got, I'm GUI demo, and, I've got a few things in the engine context here, and I'll talk about how I want things to be done later, but for right now, like, why I'm sort of redoing this is I've made things too complicated, and they need to be simplified because this is not a complex game. And I don't want to be working on this for the next 10 years, right? I don't want this to be like everything I've been working towards. And so we're also seeing some stuff that I've added for the platform API, in that, the platform likes to work in pages, right? So there's basically, there's like a boundary where we should be contextual about where our pointers are. And so these arenas, right, they're allocated they're committed on page boundaries. And the allocation granularity isn't really all that important. It's just like when I'm reserving some memory, it has to be a multiple of like 65K or however much that is, 64K. But it basically queries the platform API to figure out, hey, what are the constraints of the memory on my system? Like, what are the boundaries things like to be, reserved and released and committed and decommitted from? And these are just nice numbers to remember. So what we say is an arena is going to be a minimum of 4,096 bytes. Okay. So, but with that, we're going to be doing some stuff, and this isn't really a day where we're going to be like taking a grand tour of the library, but or rather the code. But what I want to do is sort of show what the startup looks like. What does this look like from a, like, what's the overall logic? How does it work? So we've got our main entry point here in, IFB 132 main. And we basically say, we're clearing the Win32 context, which is just a structure that contains everything. I like to store these arguments because, they are used by the like window management system in Windows. Like, I know the H instance is used, so I get the platform API and I initialize it, which is just basically a bunch of function pointers to allow us to request those resources, and I'll show that next. But we basically create the engine context, pass it the platform API structure, which again is just function pointers, callbacks. We start up the engine, and while things are running, while the engine, has a heartbeat and it's like, yes, we can execute frames, we are going to update the engine and update and render. That's all that there is right now. There's really not a lot to it. And here is what the platform API initialization looks like. And these are the function pointers that make it possible. So we have a system API, which is where we get our page size, allocation granularity. I'll add some time stuff for, like, getting the current milliseconds and, sleep for a certain amount of time. And so here's the ones we're going to be working with today, right? So we're using these semantics, right? To reserve memory, to release it. And remember, we're only calling these. Reserve is called immediately on startup, and we call it on shutdown. We basically say, hey, I need this memory. Give me a big continuous set of addresses that I can use when I need some memory, and then return them, say I don't need them anymore when we shut down. Like the Win32, the operating system handles that automatically, so you shouldn't even have to call release, but we're still going to do things proper. And then commit is like, okay, so if that big chunk of addresses that I've reserved, I want to, commit an arena or commit pointers. Like, the platform doesn't have a concept of what an arena is, but it's going to say, commit and release, right? That's it. So, anyway, what I would like to do is sort of refactor the memory API right now, because right now it's internal to the engine, okay? So I've got a lot of function stubs here in the header file, and so we're probably going to be redefining a couple of these, but I want to start simple, okay? And basically, just getting that reservation is, what we want to do right now. So, we will need a reference to the platform API. So, what we're going to do for right now is, we're just going to make a new folder, and it's just going to say memory, right? And what I'm going to do is I'm just going to say ifb memory.hpp, okay? And I think I may have this in common, maybe? Yes. So this is going to be a little messed up, but hell, I may just move that. Yeah, let's just go ahead and do that. I'm just going to delete this. Yes, delete. And I'm just going to copy this and move it here, okay, to the memory, right? And now I've got a bunch of stuff in here that I don't really need, okay? So what I think I'm gonna do is just remove a bunch of stuff, right? And this is probably like, you know what? We're just gonna start over. I'm feeling good about it, okay? Just, fuck it. We're gonna do it live. So, what I think I'm gonna do now is just say ifb memory, right? You know what? No, we're gonna call it a memory manager, okay? And so here's our memory manager, and what does a memory manager consist of, right? Well, we're gonna have a memory reservation, okay? And we know that a reservation is divided up into arenas, right? Right? And we know that there are allocators that we're going to use to continue to utilize that memory. Now, you can use an arena's memory directly, but this sort of helps provide ways of continuing to manage that memory. So what we're going to do is we're going to say, okay, IFB memory stack allocator and block allocator. So that's what we're going to do here, okay? And I'm thinking of how I want to continue to do this. So I think for right now, let's talk about our reservation, since that's the one that's kind of like the heart of where everything starts, right? So here's what we got going on. So I like to work with addresses because, well, with addresses, things are never going to be null. As in, you can't, like, dereference an address. It's just an integer, right? And I'm trying to think of what the best way to do this is. Oh, something else that I didn't talk about is having a global stack, right? And that's actually before the reservation. And I'll talk about that in a minute. I'm sort of doing this backwards, I think, from how I should have, like, talked about this. But this is more like static memory management is very easy. Like, you just say, hey, here's a block of, like, here's literally an array of bytes that I am just going to have at compile time. The compiler is going to say, hey, whenever this program is executed, I need a stack size of X because of the stuff that I have in there. And so you can literally just declare a array of bytes and it'll be on the stack. And that stack memory is available to you. It's not something you have to deallocate. You would still have to manage it, like, as in continue to subdivide it into regions to use. But I will sort of go over later the uses for it, like how I want to continue to do that. So, but right now we're just going to start with the reservation, okay? And so, because I like to use pointer, like, you know, basically pointer arithmetic, where I just have one single pointer or address, and everything after that is just sort of, like an offset from that. Because storing a small offset takes up less memory than storing another pointer. But let's just say for now, you know what? I'm just going to call it an address, okay? And I may as well go ahead and show what my types file looks like. These are simply redefinitions of types, like, you know, standard integers like int 8, int 16, int 32, and, you know, uint for, unsigned integers. And the reason I like to do that is because if I'm sticking to these types, I always know where a variable came from. Does that make sense? Because, can I do like GL int? Yeah, so OpenGL does exactly the same thing. And it has like GL int, GL size, GL boolean. And doing things this way, it may be a little pedantic, but it's a way of tracking. I know exactly that if I'm looking at a GL int, then that number was assigned using, or how it assigns context to a variable. Does that make sense? Like, I'll always know that this is being used by OpenGL, and my IFB address and IFB integers, I always know is going to be, it came from it flies by, right? Of course, IFB meaning it flies by. So here's how I like to do this. There's a start, and because we'll also say size. Now, 4 gigs is the maximum size allowable by 32 bits. But it could potentially be larger than this. Maybe, we want to add like a massive amount of debug tools for what's supposed to be a simple game, and we require more than 32 bits, or more than 4 gigabytes. So, the maximum for 64 bits is 8 terabytes, which we'll never hit that. I hope to God we'll never need that. We won't. I'm just trying to be funny. But it basically has a start and a size. And, like, that is the crux of our reservation right there. That's it. And we'll have, things that we want to do, like, we'll just say IFB memory is the namespace. And you know what? I don't even need... No, I don't need that. I don't think I do, anyway. Because I've defined basically a pointer to a byte as memory. But... And I like having it, but by looking at that, you sort of lose context that it's a pointer. So what I think I'm going to do is just remove it. And what we'll say is, we're just going to say reserve. And this will take in a pointer, right, to memory reservation. Now I remember. So, what we want to know is the page size and the granularity, right? I'm thunking. I think what we want to do is, in, let's say, userland, we'll just say for the memory manager. Because the memory manager is sort of like the parent structure that contains everything, right? So the memory manager is going to have a single reservation, okay? And right, like, there is our memory reservation from our platform, and there we go. We're off to the races. So what we need to do next is, I may even say, I'm debating on if I want to pass in the memory, I think I will. So here's what we want to do, right? When I want to initialize the memory manager, I will pass in the platform API for memory, so we can manage it, right? So IFB memory, and what we can do is say memory manager create, right? and we'll also say memory manager destroy. And how I like to do things, like with functions, is I follow a syntax that's like, the syntax I follow is verb, or noun, verb, right? So I have the thing, which is the memory manager, and then the action that I want to do with it, right? That's just the syntax that I take when I code. So, of course, we'll have the memory manager itself, which we will have a pointer to, right? And I'm debating how we want to do this. I could just say pass in a reference, but then that sort of puts us in a box for however the... Yeah, I think it's just going to be a pointer. And that's it. Okay, so... memory manager pointer. And so we'll say, you know what, user or programmer, whoever is using this API, you are responsible for whatever it is that you want to do. You can just have a static reference to this memory manager and pass in the pointer to it, or you can allocate one yourself however you want. But whatever memory is managed at this point, using this is how it's being managed, right? These are your options. So, and again, I'm thinking, how do I want to do this? So, what we can do is say, memory manager reserve, or say down here, we say memory reserved, and then we say memory release. And up here, I forgot, we want to notify the user if what we did succeeded or not. This is a very C-style API. And a B8, as you can see over here, is just a Boolean. So, how do I want to do this? See, this is one reason why I didn't want to do a live stream, is because I'm thinking. And it doesn't really make sense to just watch someone think about this kind of stuff, right? And I'll at least try to get some stuff hashed out for like at least the reservation, and maybe kind of like how arenas are divvied up and those kinds of things. But what we're gonna do here is, again, say that at this point it's probably safe to pass in references, because I have access to a memory manager, however the user wants to allocate that. So what I can do now is just say, hey, I want to reserve some memory. And maybe up here I will also say, I want to include, you know what, this is a separate library, so I think I'll just say we're gonna include, there we go. And so now we should have access to the platform API. And for these big functions that are like create and stuff like that, I kind of like to syntactically, do them like this. So what we'll say is, we'll pass in the pointer for that, and then pass in the lat memory API, right? We don't, that can, do we want that to be a pointer? Because we're essentially making a copy. Yeah, let's just make it a pointer for now. Right? So that's what we need, and we know that we're gonna need access to that, right? May as well put that first. That's just what's needed. So, I don't know if these... Honestly, I don't know if a lot of these functions are even necessary right now. I'm just prototyping some stuff. And I thought I was on Do Not Disturb. I am. That was just some other notification that went off. We'll just leave that here like this for now. I may not even need these. So this is just sort of a rough draft. This is one reason I love C++ and C, is because I can sort of hash out things that I want to do using header files. I can get an idea of what I want this API to look like. Guy, come here. Quit the borking. Quit borking. But, we can also say const, well, yeah, I'm not getting a pointer back, I'm just initializing the reservation, you know? So... Poor girl. Yeah, she's just not happy. I don't know if anybody can hear that, but yeah, daughter is just really not having a good time right now. My wife was willing to watch her for a little bit while I just kind of do some stuff. We've just been running around the doctors like since Friday, and everybody's tired. So, I am not sure what I want to do here. The memory manager is a very nice place to kind of reserve everything. You know what? Let's just pass in the memory manager, right? So... right, we'll just say memory manager pointer, and I'll also say API pointer. And so what we want to do is we want to say you know, basically all that stuff that's in the reservation, right? What is, you know, all of this, essentially, right? So what is the, you know, what's the size, what's the, you know, page size, what's the allocation granularity, all that jazz, right? We could also say what's the minimum arena size. No. I got an idea. Hold on to your hats. It's always, whenever I say I have an idea, just brace yourself, right? So, but here's what we got, right? And so, this will give us a reservation, okay? And for now, within the context of what we're doing, like, you could theoretically have more reservations. You can make as many as the operating system will let you have. But within the context of the problem we're trying to solve, which is, I need a contiguous set of addresses. What is the minimum amount of steps I need to take just to give me that one contiguous set of addresses. You may as well only make one, okay? So there's that, right? And so memory release, it just takes in the one function, that's it. And also we can make these constant, like this. Because these will not be changing, okay? So we'll just make those constant and go from there. Now we get to the fun one, the arena. This is the part that I like because we actually get to think about, you know, how do we actually want to structure this, right? So, and what I'm thinking is this will be a linked list, right? So an arena will basically just store a pointer to the previous and the next arena, right? So a double linked list. But if it's immutable, it doesn't need so I'm just gonna quickly define what an arena is gonna be, right? And so remember I said, you know, a page size, right? And so what we're gonna do here is we're gonna say page count, right? So an arena is gonna span a certain number of pages. This ensures that by doing it this way, it's always going to be a multiple of the page size, okay? And we can also say, you know, it's also going to have its own address. Or, to even shorthand that, page number. Right? So, for instance, if it's page 0, then we know immediately that it's just, you know, the start address plus 0 times 4096. If it's page 1, it's base address plus, you know, that. So we know immediately that, you know, we have some stuff that we're storing without actually having to store pointers. Because pointers are just awful. Like it's like chasing pointers is bad. So like let's just avoid doing that where we can. So what we can do is say well, we already know that we're doing this. We're making this a linked list, right? So next. It's going to store a pointer to the next arena. Literally, as I say, pointers are terrible. Don't use them. But I will go into my design choice for this in a moment. So if I know the number, like which page does this start on and how many pages does it have, I can immediately calculate the offset from start. And that's really all an arena is. It is just a fixed sandbox. We have like this fixed dimension. We have this fixed, you know, boundary within our reservation, and I should change this to arena, that we know things are going to happen in and pull from, right? I'm thunking. There probably is a way to make this a linked list in a more data-oriented way where it doesn't store a pointer, but rather it stores a handle to the next one. We could do that. But for now, let's just keep on trucking. And let's hash out the functions for an arena. and we'll go from there, right? So I want to save memory, arena, commit. And remember, these are immutable, okay? So, and what's going to happen here is we are going to get a pointer You know what? I'm starting to think that there's no reason to do that. Because no, let's just keep doing this, right? It's not going to return a constant because this right here, this pointer can change. Right? And so we commit, and we could just say, to make it easy for whoever's using this API, what we're going to do is we're going to say, okay, first give us the memory manager and say, like, arena size minimum. And so what we can do is, so the user doesn't have to calculate, oh, well, how big is a page, and, you know, how many pages do I need? What we can do is just, I've already made some macros for this, and basically, we'll just round up to the nearest multiple of pages, and we'll go that way. And I'll also do this up here in the reservation. We'll have that size, and, like, it's not gonna change. Like, what I can do is I can say pages committed and pages available. Give you 32 pages available. Oh, no. I've got it backwards. Pages total and pages committed, right? And so you could just walk the linked list to get that total, but it's like calculating like the total and committed is going to be a very uncommon operation, and it's going to be expensive to walk a pointer chain, so let's not do that. We have, basically, we're committing an arena. Here's the minimum size we want it to be. That's it. That's all an arena is. It is just a fixed, constant region, subdivision of our reservation that we get to play in, okay? And that's it. Now, here comes the problem of what is a, where does this pointer come from, essentially? And, like, where are we getting this? Because it has to come from somewhere. Something has to commit it. And so this is where the global stack is going to come from, right? And so with that, let's go back to the whiteboard. To effectively utilize this, what we need to do is say, we need something global, right? So with this, we're going to be talking about program memory, right? So you have something called a stack. Actually, let's do it like this. Let's go back. Let's use our handy dandy rectangle tool. And it works like this. Oops. It works like this. There we go. And so this region right here is the stack, okay? Actually, instead of doing that, why don't I just Google it, right? Let's see, program, memory, no, this is the wrong window. So why don't we pull up our other window, yes, our guest window, and say, let's say, 132 program memory, not program memory, program memory layout. Okay? It's gotta be in here somewhere. Ah! This is a good representation right here. Okay? So, let's get rid of this shit. And I was about to say, if that was going to be the size of that picture, it's just like, oh my god. Okay. So, whenever a program is executed, there's a lot of stuff that's going on in the background, right? And this right here is what it looks like from a very high level. I wish this was in dark mode, but you have there's a lot of stuff that's going on here. But the two memory structures that we care about are the stack and the heap, okay? So the stack is a fixed size and it's fixed at compile time, right? And so we'll just say stack and heap. Okay? So the stack, fixed at compile time. We'll just say compilation. And it is very fast, right? It is blisteringly fast, right? Maybe not blisteringly fast, but accessing the stack is much faster than accessing the heap. And I'll explain why in just a moment. So, and it's always constant, right? But here's the problem, because it is, it's limited, right? However much you have, and the stack is however much you have. I can't remember how much you normally get, if it's like kilobytes or a megabyte or two, but it's not huge. But there are command line arguments you can pass into a compiler to say, here's how big I want the stack size to be, okay? And it's not like there's like a, like how you access that within your program is you just declare global variables. That's it. Like, you can say, whenever you declare something a static const, that's gonna be allocated on the stack, right? And so, if I say static const, memory manager, and I have a macro that says, here's how big I want the stack to be, it'll just basically pull that from my program stack memory. But you can overflow it, right? Because it's fixed. So you have to keep that in mind. Keep that in context. So the heap is dynamic, right? And so this is where I will use the rectangle. I'll just say, I got it. The heap is dynamic, okay? And so remember that illustration I did up there? Like, you allocate this, and then you allocate one of these, and then, okay, I deallocate that, and I sub-allocate one of these, and then something like that, and it's very slow, right? It's very slow, because this is the stuff that happens whenever you call new, delete, malloc, free. It's accessing the heap. And it is slow because a lot of this stuff is managed by these pointers are managed by the operating system. You have to do bookkeeping in order to remember, like, okay, this pointer was allocated at this time, and whenever I call free, it's this big, and I need to remove that much whenever I call free and return it back to the operating system. That would also mean new, delete, malloc, and free are very slow because they switch from user mode into kernel mode. And it's also error / fragmentation prone. Right? So, like I said, a lot of these pointers are managed by the operating system, and over time, like, this becomes fragmented because, like, you're newing stuff, you're freeing stuff, and sometimes, like, enterprise-level applications, they can have thousands or even millions of calls to the heap using, you know, new and delete and free and malloc and free. And over time, it gets even slower, right? Because it wants to find a place to put memory. It tries to keep things as compact as possible. So instead, it's like, I want to fit something over here, or like, it can put something over here, but if I have empty space, like right here, it'll try to put it there, right? But searching through this and keeping track of it, it's infuriating, right? Don't do that. Which is, instead, what we're doing is we are just bypassing the heap entirely by just mapping pages of RAM directly into our program. And that's what the virtual memory API in Windows allows us to do. So that's what we're doing instead. We are just not using the heap at all. But, like the concept of an arena, if we have a pointer to an arena, it's got to come from somewhere. And that's where it'll come from the global stack. So what we do is we just basically push size of arena, and we'll just update our stack pointer, and we will get a pointer to an arena. So now we come to, like, why use one versus another, right? So we have basically our global stack, and instead of a heap, we have our virtual memory. Virtual memory reservation, right? VMR. Is that something I can patent or something, or trademark? I don't know. Maybe I could use it in It Flies By, I don't know. Why use one versus another, right? So remember, this is also kinda dynamic. And it's sort of like, and this is fixed, right? And what I mean by kinda dynamic is, like, I have custom allocators that are managing regions of that reservation, right? They are, like, pushing stuff, pulling stuff, resetting, you know, acquiring a block, releasing a block, those kinds of things. So, but the stack, the global stack in the memory manager is fixed. So, I can't pull from it, I can only push to it, okay? So they're both within, like, program lifetime, we'll just say that, you know? We have one and the other. So, rather than just work through all the theory, what I'm going to say is this manages collections. Okay? And the global stack manages singletons. Okay, Sam, what the fuck are you talking about? What is a singleton? A singleton is a one static instance. You could also say just a single instance, which is another way of saying only one of a thing. For instance, in this game, there's only going to be one window, right? Within the graphics system of our game, there's only going to be one window that has only one renderer. Okay? So, as an example, there's single window, which has a single renderer. There's also a single sound system. And there's a single physics system. Okay? So these systems and these managers, there's only one of them. Okay? In each context, there's only one. Okay? So if there's only one, we don't really need to do this fancy, like, arena type shit. We just push them onto the stack and just say, hey, I need a quick allocation. It's a fixed size, there's only one. I'm never gonna need to undo it. As in, like, remember, lifetime. Contextual lifetimes, right? The contextual lifetime of a singleton is for the entire execution of the program. That means from startup to shutdown. So, just push it onto the stack, right? And just reference it. And here's something else that's cool, right? So let's say my stack, right? It's an array of X bytes, right? And we'll just say a U8, right? So when I allocate something and I push it onto the stack, this right here, my pointer, can just literally be an int. If it's going to be less than 4 gigs, could be larger than 16,000 bytes, so 16K, but just make it an int 32. Make it it's literally an index in this array. So now, like, a reference to my window becomes an int, this becomes an int, this becomes an int, this becomes an int. And so now I can just say, hey, give me the instance. I don't have a, it's like if I want the pointer for it, I don't have to store the pointer. I just say, here is my index to the window, the stack index to the window, and give me that back, and we're off to the races. So that's where singletons, where the stack would come into play for managing singletons, where I only would ever have one of these things. I'm not going to have more than one renderer. I'm not going to have more than one sound system. I'm not going to have more than one physics system. But now a collection. Now a collection is pretty straightforward, right? What's a collection? List, array, even a tree. And, you know, like other data structures. Stack, queue, queue, etc. And this is another way of saying lots of things, right? It's literally the exact opposite. But I don't really know how many I'm gonna use at a single given time. But if I'm making an allocator that's pulling from fixed memory, I should be able to calculate like an upper bound. Like, what is the upper range of things that I would be working with? But collections of things would be like, let's say, you know, positions. We'll just say example again. Sound samples. sprites, vertices for the renderer. Like, basically, it's like, is it plural or singular? If it's plural, as in I'm going to have a bunch of these things, we're going to create an allocator for them that pulls from a memory reservation / arena. If it's singular, just push it onto the stack, and we have an index for it. There you go. It's as simple as that. And so, while I do have a bunch of arenas are distinct, right? Arenas don't overlap. And so, I just basically push a arena onto the stack and just return it. And that's how we can do that. We also gain the benefit of potentially making the reference to an arena opaque, because pushing it, like, if I just say, hey, here's an integer, then I can just, type def that, or basically say struct, stack index. Now, this becomes type safe, right? Nothing else can go in there. So with that, let's go ahead and start working on the stack, okay? And I'm going to be wrapping up here in about 10 minutes, but let's go ahead and think about that, okay? What do we do? What do we reason about, the stack, okay? Let's go ahead and make a nice little spot right here, and we'll say global stack, okay? And I'm not really worried about making, references opaque right now. And by opaque, I mean, like, stuff over here, using handles instead of pointers that can be directly dereferenced to their proper types. But in the future, I may want to do that, because you could easily, like, let's say if I have the memory manager and the memory reservation has very sensitive bookkeeping information in there, changing the value of something in there could really fuck something up. And you don't want to do that. So, but what we can do now is just say, we're not worried about that. We are just worried about making something work. But, premature optimization would be trying to figure out how the handles would work in this context. Do I want to make it an index? Do I want to make it a void pointer? All we're worried about right now is just setting us up for success with how we want this to work. Okay. Premature optimization is also another very abused term. Like, premature optimization would be like implementing SIMD or something like that without actually doing the cost analysis of, like, if actually, doing the operation to set up the SIMD registers is actually worth the time. But this is just engineering. I fucking hate the term premature optimization, because it's a way to say, oh, I don't have to, actually doing my job is premature optimization. No. Like, this is engineering. It's not premature optimization. Rant over. So what we can do is the global stack, like we said, is going to have a byte, which, remember, it's just an int, right? And it's going to have a size, right? So we can just say define IFB. Gaia, come here. You are fine. You lack nothing, girl. Okay? And so we should also have macros defined, and right now... But, sweetheart, quit that. Come here. I think Guy is trying to tell me to wrap it up. But what we can do is we can say macro size megabytes. And we'll just say 64. Okay? And this is I have a macro file, macro header, which is like, these are my global macros. and I like to put sizes in there, right? So we'll just say for now, the global stack is 64 megs. That's huge. And it should be bigger than we would need. You know what? I may even make it smaller. You know what? Yeah, let's make it a challenge. We need to fit everything in 64K. I like it. I like it. And so this is going to be an array, and it's just going to be stack mem, or yeah, we'll just say mem. That's not verbose enough. Sam it up. Make it as verbose as possible. We'll just say static memory. Or byte array. There we go. I think that's enough. So, we're not gonna have... I like having some context here. So I'll say, size. And this right here is gonna be, position. Right? And so what this is the actual... I was just making sure a guy was chewing on an actual toy and not, like, an appliance or something. So the position is going to be, like, how much of the stack have we used? And so whenever I say push something onto the stack, it just gives me the index back, and it updates the position accordingly. So this is just really, really simple, right? So... memory, and I'm gonna wrap up here. I'm gonna try to wrap up here really quick. But what we do is we have memory global stack push. Global stack push. And it's gonna be size, right? And there's also the concept of alignment, right? So, I think that's beyond the scope. I don't really have enough time to explain the concept of alignment, but things like to be aligned on powers of 2, right? That's how the computer likes to deal with memory. So what we can do is say stack push aligned to just give us some more fine-tuned control over how we do that, right? And so we can say alignment, right? So, and what this is going to do is this is just going to return us, we can say IFB memory stack index. Stack handle. How do I want to do this? This is getting kind of nasty. I see memory global stack index. You know what? Let's shorten this. We already know it's global from the context, right? We can just say stack. And, excuse me. We can say, does it have to be global? And I still like the idea of making, pushing it on the program stack, because it would still be faster to access that than a pointer returned by the virtual memory API. So, what we can do is we can just say memory stack, right? And we'll say memory stack index, right? And so what that is it's literally just we'll just put that there, right? or just say value. You know, what's the value of that index? I think my daughter's knocking at the door. And so these are global, or these are constant, rather. So we can just say stack index, and we can just say this returns directly. It's just a number. It's a value, an integer, basically. So that will return that, and that gives you an index. But we also need a way of getting a pointer, right? So what we're gonna do is say we want to get a pointer back. Global stack get pointer. Okay. So we pass in the manager, and we also want to pass in one of these, right? And so the benefit of doing this is we know right now that that's type safe. Okay, so it's just a little bit of extra added security. So I'm debating on, no, I like this because it adds context, right? And that's the thing, is it gives us some context as to what's going on, right? So yeah. So that gives us that, and we also need to do something like this, where I have the memory API, but we want to put the global stack first. And I don't really need to say global stack anymore. Wait a minute. I'll just say memory manager here. I can say AFB memory stack. We'll just say stack. I still think that needs to go first, just because, size up and everything. We want everything to be aligned. Something else that a lot of people don't realize is that the position of your variables within inside of a struct also determines how big it is. So basically, everything's going to be aligned by the first data type. The more you know. So we have the stack and we have the reservation, right? And we have at least the stubs for creating this. And what we could do is something like this. And I don't know what I want to do. But we know that an arena is going to be on the stack, right? So what we could do, arena ID just inherits from the stack index, right? And there you go. Now, what we've done is we've added some extra safety by type defing. By struct this, we have type safety. And we've now made this an opaque reference. There you go. And we can make it constant, and now this shouldn't ever change. Okay? But if we're doing that, we also need to expose these things right here, right? So like memory arena get page count, and what you're gonna need is these are gonna be const get 32s, and like, you get the picture. Like, it's not really anything earth-shattering here, but we've and if we're doing this, we may as well do that, just to say, here's the ID of this arena. And so basically what we do is we just pass in a const arena ID. And so this will just return us the page count and the number, right? So, and we can also just say get size. And for our allocators, we can do the exact same thing and just have a thing in there. Oh, and now we can do this because now we don't need it doesn't need to be a linked list anymore, so we don't have to chase pointers, right? So what we can do now is just say bam, something like that. So now what we can do is, so the first arena, if I've got this right, if you know, I'm hoping the math, the logic is logicking, the code is coding, the program is programming, brain blast. So you get an arena and it returns an ID, which is essentially an index in the stack. And so this one would be, you know, whatever stack position it is, and the next one would be 0. There also needs to be an invalid stack ID because, let's see, define if the memory global stack index invalid would be basically the same thing, right? So, when it's created, it'll have that invalid number in it, and so when it's actually assigned, when one is put in there, we'll just say it's that. I know I'm all over the place right now. My brain's not working. But what we've done now is instead of like constantly dereferencing pointers, we can now directly index the stack. Bam. I think with that, I'm going to call it, because I think it's plenty of stuff, and my brain is just fried thinking about this. But I like how this is turning out. So, if you're watching this video, thanks for watching, and you know, I hope you learned something. I hope you were entertained, and my dog is very bored and wants to go play. So, with that, I'll see you in the next video. Thanks for watching.